For our bifocal model, we wanted to model the rate of yeast metabolism. So usually a real-life yeast can convert sugar into energy and produce carbon dioxide at a certain rate. But if you're using yeast for baking, for example, using active dry yeast, when you wake it up, initially all of the yeast inside this packet are dormant. When you wake them up, they start producing carbon dioxide, but at a lower rate. So it takes them a while to get up to full metabolic strength. So we did a bit of background research and realized that the rate of change of the rate of CO2 production is actually linear. So we wrote a model that is going to run regression on some sample data of CO2 production and be able to figure out what's the actual rate being exhibited in the real world. Okay, so we have one version of our NetLogo program that runs on simulated data. If the real world were nice and clean like this mathematical model we were using, our model would be able to have an initial hypothesis and then converge exactly to the correct noise-free data. So if you notice, we have on our screen a picture of a little contraption with water and yeast sitting on top. When we hit setup, it actually models all of this for us. And then when we hit go, we're going to be able to see the amount of CO2 in the system as well as the rate of CO2 production in this graph over here. So when we hit go, so over here the green is showing what's actually happening in the model, and the red is showing what's happening in the real world. So our real simulated data is actually pretty far off from what's actually going on, but every 10 ticks we're going to run some regression and converge to the actual curve we're seeing. So you notice over here that we're pretty close to the real thing after just one level of regression. So with noise-free data, we actually get a really good idea of what's going on in the system. So when we set up our physical model, we have a bottle with, it's sealed at the top with our CO2 sensor, and in here is a mixture of yeast and a little bit of simple table sugar, and then we add a bit of the active dry yeast into it and mix it up. So right now it just looks like a cloudy solution because nothing has happened yet. All of the yeast isn't quite awake, but soon we should be seeing some blooming in which the yeast is going to wake up, start producing CO2, and float some foamy stuff up to the top. Check it out! This is yeast. This is how yeast blooms. So all of the cells are sitting at the bottom of this container, but as they wake up, they're burping out CO2 and floating some fluff up to the top. Alright, so here's our model on real data, real noisy data coming from this sensor. So the deal we've had with this sensor is that it produces kind of oscillating signals around the actual level of CO2. So we're having to take an average of what we're reading from the sensor at any point in time, and that's introducing a lot of noise into our model. So if we look at it here, we can set it up exactly the same way, and we hit go, and our model has some idea of how to produce at some internal rate, but if you notice, it's very far off from what's going on in the actual model. Ours looks nice and clean, and here's this, little messy curve from what we get from the real world. But every time it is, after 10 seconds, it is correcting itself back to what it's seeing in the actual world. So you notice here we can see all these weird oscillations. But gradually the CO2 level is picking up, and we are picking up on that as well.
So the most difficult part of this project was actually the electronic components. So we have this Pasco sensor, CO2 sensor here, and we had to figure out a way to connect it to the GoGo board so that we could actually connect it to NetLogo and our computer model. So after a lot of frustration with the breadboard and testing out with different alligator clips and the multimeter, we realized that when we were testing the sensor, we weren't actually getting any power through the sensor. And to fix that problem, we realized that we actually needed to have a 5 voltage power source and a +12 and a -12 source, all connected to this Elvis adapter, which then connects the sensor to the GoGo board. So once we figured that out, we still had one more problem. There's actually this little pin on the GoGo board that connects a circuit inside the GoGo board, which has a resistor in each port. And so most sensors actually have a resistor in them, and the way they work is that the resistance changes depending on whatever you're measuring. But this CO2 sensor actually works in a different way, and when it's plugged into the Elvis adapter, it just outputs the analog value directly. So we needed to figure out a way to remove that circuit connecting the resistor inside the go-go board to just get the analog values straight from the sensor to the go-go board. So we actually had to remove this little pin that we saw on the sensor. So once we finally got it working, it was really exciting, and we felt rather proud of ourselves.